All right, you guys good? Questions? No? Okay. Well, in that case, right? In that case, we'll move on. Cool. So topic 6. Topic 6. Plane motion of rigid bodies, which is kind of what we were doing before, but this time, right, just like we did our progression through particles where we started with kinematics and we did Newton's law, and then we did the kinematics of of particles, and we did the kinetics, right? We did Newton's law, we did impulse, and we did momentum, right? So now we're going to do energy, impulse, and momentum for rigid bodies. So how do we deal with this rigid bodies, right? It turns out that the method of work and energy, the method of impulse and momentum can be used to analyze planar motion of rigid bodies of systems, right? So the equation doesn't change. Remember, this is a scalar, right? Work is a scalar. Energy is a scalar, right? Meaning that it doesn't have directionality, right? It's just the amount. We're talking about the sheer amount of energy that we have, right? So we can apply this to a rigid body, right? Whereas in particles, we were talking about simply the translational energy, right? We're talking about the kinetic energy due to translating 1/2 mv squared. And we were talking about the kinetic energy or the potential energy due to moving in a gravitational field, right? Well, potential energy is not going to change. But if we have something that's both rotating and translating, we need to account for all of that kinetic energy, right? So if you throw the football, right, it's got some rotational kinetic energy because it's spinning slightly, and it's got translational, right? So both of those things lumped together. So how do we do that, right? Can we just add them? And the answer is yes, because the units line up, right? We'll talk a little bit more about that in a second. The principle of impulse and momentum is given here. And we talked a little bit about angular momentum with particles, right? Because if you have a system of particles, you can calculate the angular momentum of the system of particles, right? But you have to pick a point. Well, we can do it figure out angular momentum for a rigid body, right? And typically we'll pick the center of gravity as that point, but sometimes we don't. Problems involving eccentric impacts are solved by supplementing impulse and momentum with the coefficient of restitution. The building blocks haven't changed, right? We've got principle of work energy, we've got impulse and momentum, right? So the initial translational momentum plus the sum of all of my impacts or impulse forces, right? Which is my force, the sum of my forces times T is equal to my final translational momentum. Similarly, the sum of my angular momentum about some point O plus all of my moments about that point times time is equal to the sum, or is equal to my final angular momentum, right? We can always use coefficient restitution. Here's a handy flowchart. So we have these three approaches, right? We've got these three things in our toolbox. And if you're asked for forces and accelerations, you should try Newton's second law, right? That's what we just finished doing. And those problems sometimes get pretty long, right? Sometimes they get pretty long. We can talk about work energy when we have velocities and displacements. So if you're given velocities and displacements, then think about using the principle of work and energy, right? Which says that the energy, the kinetic energy, state one plus the work that it takes you to get from state one to state two is equal to the final kinetic energy. This becomes simplified if we have conservation of energy, right? If we don't have any non-conservative forces, we can conserve mechanical energy, and that this becomes T1 plus P1, right? So potential energy plus the kinetic energy at state one is equal to the kinetic energy plus the potential energy at state two. And finally, impulse and momentum, right? If you ask for velocities and time, this is where we want to be. And we've got two equations here, right? We got one for translation and one for rotation. Same deal with Newton's law, right? Deal with Newton's law. Turns out that the Sharpie impact tester, which we use to determine the amount of energy absorbed by a material during impact, does this, right? So it creates a collision, and then we measure the deformation of the piece of metal, right? Or whatever material is in there. To determine the amount of energy absorbed, the final gravitational potential energy of the arm is subtracted from the initial gravitational potential energy. Okay. Where are we at? So principle of work and energy. Work and kinetic energy are scalar quantities, right? So today is going to be all about work and energy. Right? So these are scalar quantities, meaning that they don't have direction, they only have magnitude. We can assume that a rigid body is made of a large number of particles, right? This is something that I've said a number of times, right? We can consider a rigid body to be a collection of particles that are all constrained to move together, right? Which is why we learn about systems of particles, because a rigid body acts like a system of particles, right? And if we assume that, then the total kinetic energy, right, the initial and the final total kinetic energy, and when I say total kinetic energy, I don't mean we're adding state one to state two. I'm saying that the total amount of rotational and translational kinetic energy are added together. And the total work due to both forces and torques are added, and the external forces acting on the body. Okay. The internal forces here, right, are equal and opposite. Right? So the net internal force is zero, right? They're equal and opposite. That's fine. All right, let's watch a video. Scalars and vectors.
In this video, we're going to talk about the difference between a scalar quantity and also a vector quantity. So when you think of these words, what comes to mind? What is the difference between these two terms? A scalar quantity is something that has magnitude only, but a vector quantity has both magnitude and direction. So if you think about the word magnitude, basically it's the size of something or its numerical value. Direction it carries the idea of something traveling in a certain direction, like east, west, north, or south. So here's a question for you. Distance, is it a scalar quantity or is it a vector quantity? So think about it. Distance is a scalar quantity. If a car travels, let's say 5 miles, you don't know in what direction it's going. So that would represent distance. However, let's say if a car travels 5 miles east, so now you have the distance with direction, which is known as displacement. Displacement is a vector quantity because direction is part of displacement, whereas distance, it's a scalar quantity. Now, what about speed? Is speed a scalar quantity or a vector quantity? So let's say if a bus is traveling at 30 miles per hour, is that a scalar quantity or is that a vector? Well, we don't have direction, so it's a scalar quantity. Now, let's say if the car is moving at 40 miles per hour north. Now we have speed with direction. That is known as velocity. So velocity is a vector, but speed is a scalar quantity. So velocity, we describe it as, let's say, 30 miles per hour east. The 30 miles per hour, that is the magnitude. That's how fast it's moving. It's the numerical value. The direction part of the vector is east. So you got to have those two parts, magnitude and direction, for a quantity to be a vector. If an object is simply traveling at 30 miles per hour with no direction, then we only have magnitude only, which makes it a scalar quantity, not a vector quantity. So if you can apply direction to something, that makes it a vector. If direction cannot be applied to it, then it's a scalar quantity. So here's another example, force. Is force a vector quantity or is it a scalar quantity? You can apply 50 newtons of force east, west, north, or south. So force has direction. You can push an object, you can push a box to the right, you can lift it up, you can push it towards the north direction. So force is a vector quantity. Now what about mass? Which column would you put mass under, the left side or the right side? Can you apply direction to mass? Can you say, I have 100 grams of aluminum metal east or 200 grams of nickel west? You can't apply direction to mass. Therefore, mass is a scalar quantity. How about temperature? Is temperature a scalar quantity or is it a vector quantity? So can you have a temperature of, let's say, 90 degrees Fahrenheit east or 100 degrees Celsius west? Direction is not part of temperature. There's no association. So therefore, temperature is a scalar quantity. It only has magnitude. It doesn't have any direction. The magnitude could be 90 degrees Fahrenheit, 100 degrees Fahrenheit. Of course, 100 is much hotter than 90. But as you can see, temperature, you can only describe it in terms of magnitude only. You can't describe it in terms of direction. You can't say it's 85 degrees Fahrenheit east outside. It just doesn't make sense. Now, what about acceleration? Is acceleration a scalar quantity or is that a vector quantity? Acceleration is a vector quantity. Acceleration tells you how fast your velocity is changing with respect to time. So if you're driving a car has a greater acceleration than a truck. Both a car and a truck can go from 0 to 60 miles per hour, but a car can get to that speed a lot faster than a truck. So a car has more acceleration. Now you can accelerate towards the east, towards the west, north, or south. So direction can be applied to acceleration, which makes acceleration a vector quantity. Now what about volume? Would you describe volume as being scalar or a vector? Can you have 50 liters of water east or 2 gallons of milk west? Direction cannot be applied to volume, so volume is a scalar quantity. So now you know how to distinguish if something is a scalar or a vector quantity. The key is to focus on direction, because both scalar and vector quantities have magnitude, but only vector quantities have direction. So if direction can be applied to something, then that something is a vector. Now, there are different ways to describe a vector. You could say that 100 newtons of force is applied at, let's say, an angle of 30 degrees relative to the x-axis. So you can you could describe a vector by describing it in terms of its magnitude and direction, which the first example will illustrate. You can also describe it graphically. So let's say this is the x-axis, this is the y-axis. So we have a force of 100 newtons at an angle of 30 degrees relative to the x-axis. So you can also describe the magnitude and direction graphically. Another way in which you could describe a force is by expressing its components. So you could say its x component is 30 newtons and its y component is 60 newtons. So let's call this fx and fy. In the graph, it looks like this. So let's say the red line is fx, it's 30, and the blue line is fy, which is 60. So it's twice as long. But because both are positive, they're both in quadrant 1. So this is f. The hypotenuse of the right triangle is the actual vector, and this is f of x. It's the x component of f, and this is fy, the y component. So let's say if f of x was negative 40 and fy is 60. Where would you draw this vector? So first you would have to travel 40 units to the left to describe fx because it's negative. X is negative on the left side. Now fy is positive 60, so you got to go up 60 units. And so f is in quadrant 2. So if you know the components, you can describe the vector. Let's say if f is 200 newtons, but at an angle of 225 degrees. So if you have to graph it, this is 0, 90, 180, and 270. So 225 is in quadrant 3. So the vector is going to be over here. And this is an angle of 225 relative to the x-axis. When dealing with vectors, you might find these equations useful. So the hypotenuse is the actual vector, f. This is f of x, f of y, and the angle theta. Now, if you have the x and y components and you need to find f, you can use this equation. It's based on the Pythagorean theorem. If you need to find the components, you can use this. Fy is f times sine theta. F of x is f times cosine theta. And if you need to find the angle, this is an acute angle between 0 and 90. You can use the arctan or the inverse tangent formula. It's fy over f of x. And if I was you, just make f of x and f of y positive, and this will give you the reference angle, or the angle between 0 and 90 that's within this triangle. And then you can always adjust the angle based on what quadrant it should be located in. But these 4 equations can help you to find missing quantities associated with vectors. So that's it for this video. Thanks for watching, and have a great day.
It's important because we're entering a lot of scalar territory right now, right? So we're not going to be using vectors for some of these work energy problems, right? Okay. So somewhat review from the last time we talked about this, right? But we can discuss the work or forces acting on a rigid body, right? So something does work if it moves something through a distance, right? And the formal definition tells us that the work from going from state one to state two is equal to the integral from point A1 to point A2 of the force times dr, right? Or if we're moving along a curved path, right, this is S1 to S2 of f cosine alpha ds, right? It's just the same way. It's equivalent. It's just whether or not we want components or not, right? So we can consider the network of two forces, F and negative F, forming a couple of moment m during the displacement of their points of application. And so, hey, what if I evaluated this, right? And I said, well, this is just F times dr minus F dot dr plus F dot dr2, right? Okay. Well, this is just F is equal to ds2, F is equal to r d theta. Well, F times r is my moment. Right, so it turns out that if you have a force couple, right, if I was pushing up at B and down at A, I would cause some rotation, right? I could replace these two forces with a moment that's equivalent to it, right? So it turns out that the amount of work, right, when we're talking about translational work, this is F times the distance that we've moved through times the change in distance, right? F dr, right? But for a moment, right, if we want rotational work, it is the moment times the change in the angle that we've seen. So if your moment is a constant moment, the amount of work to go from 1 to 2 is equal to the integral of my moment from theta 1 to theta 2 d theta, or m times the quantity theta 2 minus theta 1. Now this is important, right, because this is rotational work, right? Because u from 1 to 2 for translation is f times x2 minus x1, right? So it's important. This is an important distinction here. Because work is a scalar, to get the total energy of a system, need to add the rotational work to the translational work, right? At some point.
How do you denotate rotational work? Is it still just U?
They still just use u. Right? If you wanted to make it easier for yourself, like if you're doing a problem and you wanted to like put the subscript r on it for rotation, that's fine too. But because it is a scalar, it is typically just all lumped together because the units are the same, right? That's the thing about scalars, right? As long as the units are the same, you can add them. Right? All right, so let me ask some questions. Does the pin force at point A do any work? So do the reaction forces at point A do any work? Yes or no? So show of hands, who thinks it's yes? Who thinks it's no? You gotta pick one. Try it. Who thinks it's yes? And who thinks it's no? Okay. No, right? How do we know that? Point A does not move. It stays there, right? So there is a force there, but that force does not cause any motion, right? Because remember, what is work? Translational work tells us that it's the force times the change in distance, right? The change in distance here is 0. So we don't get any work. Does the force P do any work? All right, so we think yes. Who's got yes? And who's got no? Let's try to, we got to answer? Who's hands? Yes. Who's got no? It's yes, right? Why? Well, in this case, the bar is going to move, right? It's going to move through an angle. So you're actually going to get, if you look at the point, right, this point P, this point is going to translate, and the whole bar is going to rotate. So you've got combined work from translation and rotation that you need to work through here. Okay. All right. Does the normal force do any work on this disk? Who thinks yes? Who? No. So who thinks no? Who thinks yes? Who thinks no? Doesn't matter if you take friction. Is the normal force itself going to do any work? So who thinks yes? Who thinks no? It's no, right? The fact that there's a normal force means that we're in contact with the ground, which means we're not changing any of our potential energy, right? So we're not causing any motion from the normal force. Does the weight do any work here? Thinks yes. And who thinks no? It's no, right? It's the same reasoning as the normal force. In this, if we were on an incline, this is different, but we're not, we're on flat ground, right? And so that weight is not causing any change in position, either angular or translation. What about if the disc rolls without slipping? If it rolls without slipping, does friction do any work? So, what does it mean to roll without slipping? Yeah. It's always going to roll. You're only going to get pure rotation, right? You're not going to get any sliding of the wheel, right? No teenagers are riding the escalator behind you and pulling the handrail, right? That's not what's happening. All right. So what do we think? If it's rolling without slipping, will the friction term do any work? Who thinks yes? And who thinks no? Answer is no. And here's why. Because if this is rolling without slipping, right, then the velocity of point C is 0. And we can rewrite our work term in terms of the velocity using the chain rule.
So I guess I'm kind of confused why, because wouldn't that be like rotational work, the spinning is friction?
Good question. Well, I'll put this. So that point that's in contact with the ground is always going to be in contact with the ground, right? So point C doesn't move with the wheel. It is the ground, right? So technically that friction never moves because it's a function of the ground itself.
So you apply work to a force specifically, not like the action that like it creates?
So friction's a tricky one, right? Because friction is inherent. Friction's kind of like a reaction force, right? And it's always going to exist no matter what configuration this is in. It's think of it more as an internal force as opposed to an applied force, right? So if you were pushing on it, yeah, then you have to, like, if you're pushing at the top of the wheel, that's going to cause both a moment and a translation, right? But because friction is an internal force, it's not about how it's being applied. It's kind of a result of the fact that we're moving, right?
That makes sense. So basically internal forces can't do work then?
Most of the time. There are certain cases where they can, but for the most part, an internal force will be canceled because it's equal and opposite, right? Because if you looked at this system as a whole, right, if you put the ground back there, the normal force and the frictional force. Right now, if this is rolling with slipping, then the friction actually ends up doing work, right? And the reason for that is because if you're rolling with slipping, you're going to be rolling, but you're also going to like skid every so often, right? And that skidding action requires you to stay in contact with the ground at one point, and that's going to cause work at that point.
Okay.
Yeah.
Makes sense.
Any other questions? Okay. So we can talk about kinetic energy, right? And I've been talking a lot about scalars and how we add rotational work and translational work, right? And the same thing is true for kinetic energy, right? We've got translational kinetic energy and rotational kinetic energy. We've actually used rotational kinetic energy one time in one of those problems, right? When we had the fidget spinner problem that exploded, and we had to try, right? We did that one in class, but also on the last exam. And we had to use that 1/2 I omega squared, right? And that's what we're looking at here, right? So if you want the total kinetic energy at a state, you need to add up the translational kinetic energy, which is 1/2 mv squared, and the rotational kinetic energy. And what is the rotational kinetic energy? Well, it looks it's very similar here, right? It's 1/2 times I bar, where that's my mass moment of inertia as calculated at the center of gravity, times omega squared, right? So this is equivalent to translational velocity, right? That's my angular velocity, and I bar is the rotational version of mass, right? So it's just 1/2 times my mass times my velocity plus 1/2 times I bar times omega squared. What if you have to do one of these where you need the rotational kinetic energy? You will either be given I bar directly, or you'll have to find it using the table, right? One or the other. You guys know how I feel about I bar. Okay, we're not going to go down that rabbit hole again. All right, so the kinetic energy of a rigid body can be separated into the translational kinetic energy and the rotational kinetic energy. And you can't talk about the total kinetic energy of the system unless you are accounting for both. Right? We need to account for both the rotation and the translation. Okay, so T is equal to 1/2 mv squared plus 1/2 I bar omega squared. Okay. So we need both. And this is basically how these work energy problems are going to change from what we did before, right? Because before, we only needed 1/2 mv squared. But now, we're going to have to account for both the translation and the rotation of our rigid body. Okay? So consider a rigid body that's rotating about a fixed axis, right? So I take my potato and I jam an axle right through point O, right? And I'm going to rotate it around that instead of the center of gravity of my potato, right? Can we calculate that? Sure. Well, it's just 1/2 I at point O omega squared, right? But what is I at point O? Is that something that we can find in a table? Well, not necessarily, right? Because turns out that point O could be anywhere on this thing, right? So the tables don't account for infinite amounts of wherever point O could be, right? So how do we do this? Well, it turns out that it's equivalent to using 1/2 mv squared plus 1/2 I bar omega squared. So right, we can do this, right? But there's a way to calculate this. We're going to talk about that in a minute. And it's typically found using the parallel axis theorem. Spoiler alert. We can only use this if we have some fixed axis of rotation that is not our center of gravity, right? That's what we can use. All right, so here's a fun one. I have a solid cylinder on the top. I have a hollow cylinder on the bottom. Yeah. No. Sure. Yep, cool. All right, so I've got my hollow cylinder on the bottom, I've got my solid cylinder on the top. They're both otherwise the same, right? Both otherwise the same. The solid cylinder A and the pipe B have the same diameter and mass. If they are both released from rest at the top of the hill, which one will reach the bottom fastest? Who thinks A, the solid cylinder, will reach the bottom first? Right, so your choices are either A will, either B will, or C, they'll both reach at the same time, or secret option D, neither of them, because meteor strikes the earth before they can hit the bottom of the hill, right? A toddler comes along and kicks it off the hill, right? It's definitely not D, I'll tell you guys right now, but I'll give you the option anyway. All right, so who thinks A, that the top one's gonna reach the bottom first? Okay. Who thinks B, that B is gonna reach the bottom first, the bottom one? Okay. Who thinks they're both gonna hit at the same time? Who thinks it's D, the one that the option I told you that definitely wasn't? But he could be lying. That would totally be something he would say if it was in fact the actual true option, right? Well, it wasn't D, it's A. A is going to hit the bottom first, right? Because of the eye. Which will have the greatest kinetic energy when it reaches the bottom? Which one's going to have more kinetic energy? Is it going to be cylinder A, cylinder B, or they'll have the same? So who thinks it's A? A is going to have more kinetic energy. Who thinks it's B? Who thinks they'll have the same kinetic energy? They don't have the same. Remember, they start at the top of the hill. They're starting at the same place. They have the same potential energy to start with. When they get to the bottom, all that potential energy gets converted to kinetic energy. It's just that A is going to be moving faster, right? And A is going to be moving faster because I is equal to 1/2 mr squared for A, but B is 1/2 m interior plus the exterior radii squared, right? Oh.
So what does that mean? If they have the same potential energy and then A moves faster, like, does that mean something?
So
how does something like faster come out of the same kind of energy or push?
All right, so good question. Is that right? Oh, it's all the buttons. Okay, gotta hit all of them. All right, so let's talk about it. Okay, so what's my kinetic energy, right? So at state 1, I've got both translational and rotational. Well, I have no kinetic energy to start. I've only got potential, and potential is mgh, right? And we know that they both have the same mass because they tell us, right? So the potential energy to start with, right? We'll call this one A up here and B down here. I'll do B in red, right? Is the same, right? This has to equal state 2. And at state 2, we have all kinetic energy, right? There's no potential anymore. We have all kinetic. And so that's going to be 1/2 mv squared plus 1/2 mr squared, right? On the bottom, oh, sorry, 1/2 mr squared omega squared, right? Forget about that. On the bottom, we'll have 1/2 mv squared plus 1/2 of m times a squared plus b squared omega squared, right? So I've just put in my i's there, right? It's I omega squared. So what happens? What is the difference here, right? Well, we know that Dr. D made the claim that A is going to reach the bottom first, right? Okay. Well, let's for a second just not look at that translational, just at the rotational kinetic energy, right? If you look at the rotational kinetic energy, right, these have the same diameter and the same mass, but that lower I is the inside radius plus the external radius, right, which is going to be larger than r squared, right? And so if this term is larger, that leaves less of the total kinetic energy to be distributed to my tangential or my translational velocity and my omega, right? So this term, because a squared plus b squared is going to be larger than r squared, right? That means that I can't distribute as much of that total potential energy now to my omega and my v, right? And that's where the difference comes in.
So is it that B is harder to rotate, or is it that B rotating more but just not moving?
We can actually cancel all these m's, right? It's a good question. It's gonna be that. So it's gonna be that it's harder. I guess if you want to think of it that way, right? A is going to be rotating more, right? And I don't know if I want to say it's harder to rotate, right? It's just, let's say it's less prone to rotate, okay? Because of the way that where the weight is distributed.
Is it because like if it's like so dense on the outside, it's almost like the moment it's like the inertia is only like one is depending on that mass.
So, I mean, it's all about the distribution, right? So let's think of it, because it's uniformly distributed in A throughout the entire cylinder, you're going to get a more even rotation, right? So it's still uniformly distributed, right, in B, but it's all on the outer edge, right? So it's, I mean, what the inertia, what the I term is telling you is that it's going to be harder for you to start rotating this, right? Because it essentially feels like it's heavier, right? Because remember, I is my resistance to rotation, right? And if that number is larger, then it's harder for me to get it to start rotating. So that's what the larger I value is telling you, right?
So is it because like the center of mass is still in the center, right?
Mm-hmm.
So like most of the weight's on the outside.
Yeah.
That just makes like it different.
Yes. All right.
Just I guess for like future reference, in a circle, is the center of mass always going to be the center, no matter
Yes.
how?
Yeah. Anything that, so think about it geometrically, right? The major shapes like circles, squares, rectangles, it's really easy for us to figure out where the centroid is going to be, right? Because it's all based off of the geometry, right? So something that's symmetrical will always be dead center. So like a circle, square, rectangle, right? Things that aren't like a triangle, right? Because you know, if you look at an equilateral triangle, you've got more at the base than at the top, so it's going to pull your center of gravity towards where more of the mass is. Cool. All right. Oh, this is a good one. All right, we'll watch this video. Which one will be first? It's very applicable.
Good morning. Let's determine which of these three objects reaches the bottom of this incline first. Bo, please read the problem, and Billy, please translate.
Flippin' physics.
A hollow sphere, solid sphere, and thin hoop are simultaneously released from rest at the top of an incline. Which will reach the bottom first? Assume all objects are of uniform density.
Okay, there are three objects: a hollow sphere, a solid sphere, and a thin hoop. Their initial velocities all equal 0. Each object has a constant density, and we are trying to determine which one reaches the bottom of the incline first. That's it, right?
Billy, that is it. Bobby, please begin solving the problem.
Well, we know mechanical energy is conserved when an object is rolling without slipping.
Actually, the problem does not say the objects will not slide while rolling down the incline.
Oh, sorry. You may assume they roll without slipping.
Right, so for conservation of mechanical energy, set the initial point at the top of the incline, the final point at the bottom of the incline, and the zero line at the height of the center of mass of the objects at the final point. Initially, the only type of mechanical energy the objects have is gravitational potential energy, and the only type they have at the end is kinetic energy. Although they have both translational and rotational final kinetic energies.
Did we not show last time that the acceleration of those objects rolling without slipping down the incline only depends on acceleration due to gravity, incline angle, and rotational inertia?
That's close. Actually, it does not. The acceleration does not have to do with the rotational inertia. We showed that the acceleration down the incline depends on the fraction in front of the mass times radius squared equation.
Close enough.
Not for physics.
Right, we have to be careful here. The acceleration down the incline depends on the acceleration due to gravity, the incline angle, and the fraction x in front of the mass times radius squared equation for the rotational inertia of each object. The acceleration due to gravity and incline angle are the same for all three objects, so the only variable which is different for each object is the fraction x. Bo, what are the equations for translational and rotational kinetic energies? Translational kinetic energy equals 1/2 mass times velocity squared, and rotational kinetic energy equals 1/2 rotational inertia times angular velocity squared. Okay, so the lower the fraction for the rotational inertia equation, the lower the percentage of the initial gravitational potential energy, which will be converted to rotational kinetic energy final, the more energy will be left for translational kinetic energy final. The faster the object will be going, so it will get there first.
No, sorry, that was too fast.
Yeah, I'm sorry. What?
Okay. Look at the conservation of mechanical energy equation. Initially, each object has a finite amount of mechanical energy in the form of initial gravitational potential energy. As each object rolls down the incline, the gravitational potential energy decreases and is converted to both translational and rotational kinetic energies. The smaller the amount that needs to be converted to rotational kinetic energy, the more that is left over for translational kinetic energy.
Okay, so a smaller rotational inertia means a smaller percentage necessary for rotational kinetic energy and more left over for translational kinetic energy, and a larger final velocity, which means it takes less time to roll without slipping down the incline.
Oh, I guess we need to look up the rotational inertia equations for those three objects then.
Actually, Billy, rather than looking up those rotational inertia equations or having them memorized, I think it is better to use the rotational inertia equation of a system of particles to estimate their relative fractions in the rotational inertia equations. Billy, could you please do that?
Well, the rotational inertia of a system of particles equals the sum of mass times the square of the distance from the axis of rotation for each individual piece which makes up the object. In other words, if the mass of the object is concentrated near the axis of rotation, its rotational inertia fraction will be smaller. If the mass of the object is concentrated farther from its axis of rotation, its rotational inertia fraction will be larger. So the largest fraction will be the thin hoop, because all of its mass is far from its axis of rotation. The smallest fraction of the three will be the solid sphere, because more of its mass is close to its axis of rotation than the other two, and the hollow sphere's fraction is somewhere in the middle. That means the solid sphere will have the most translational kinetic energy left over and have the fastest final velocity, followed by the hollow sphere and then the thin hoop. So the solid sphere is the first to the bottom of the ramp, then the hollow sphere, then the thin ring.
And there you have it. The object with the smallest fraction for the rotational inertia equation, the solid sphere, has the largest percentage amount of translational kinetic energy and therefore is moving the fastest and therefore reaches the bottom first. The reverse is also true. The object with the largest fraction for the rotational inertia equation, the thin hoop, has the smallest percentage of translational kinetic energy and therefore is moving the slowest and reaches the bottom last. Thank you very much for learning with me today. I enjoyed learning with you.
Sounds sincere, for sure. Yeah, so that's why, right? So we assume that there's no friction, right? For this, because we're assuming rolling. Well, it's not no friction. We're assuming rolling without slipping, right? When we do that, would it have more friction because it's wider? It's more in contact with the surface, right? But we take that into account because it's a function of the mass, not the surface area, right? Now, friction is, I mean, it's a good idea, right? But friction is not a function of the width of the object. It's a function of the interaction between the two surfaces, right? So it doesn't matter how much of the surface you have. It just matters that the two surfaces are touching. That's what's going to create the friction. The thing that's really important for this in particular is, let me get there. Sorry, my brain's not firing on all cylinders right now. The thing that's most important is the mass and how we're distributing our mass away from the axis of rotation. That's what's most important. Now, there's a cool video. I think it's cool that we'll watch in a couple weeks. We talk about gyration and gyroscopic motion. That maybe or maybe it is and maybe it's not related, but I like the video anyway. From Vsauce on a very particular shape that actually, because of the shape of this curve, anything that you roll down it will always end up hitting the bottom at the same time, regardless of what it is. So we'll talk about that in a couple of weeks, right? It's pretty, I think it's interesting. We'll see if you guys like it. Vsauce is good stuff. If you guys haven't found that YouTube rabbit hole, right, then be glad, because there's hours and hours and hours of stuff. All right, anyway, systems of rigid bodies, right? So we've talked about all the things that we already done, right? We've got work energy, we've got impulse momentum. Well, we haven't really talked that much about impulse momentum. Right, we're still in the work energy stuff. So, right, so what if I have two things that are connected, kind of like this, right? So I've got problems involving systems, of rigid bodies that are all connected together. Can I use principle of work energy to solve this? And the answer is, well, it depends on what you need, but sure, you can use work and energy, right? And it turns out that you can split it up, right? So if you start with this system here, you can do the total system-wide energy, or you can break it into pieces and find the energy of its parts and then add them together, right? So for something like this flywheel with a mass attached, right, you could look, this is just rotating, right? The flywheel only rotates, so we know it only has rotational kinetic energy. We find that, then we find just the linear kinetic energy, just the translational kinetic energy of the mass, and you take both of those and you add them together and you have the total kinetic energy of the system. Right. Well, I mean, I guess technically the mass itself would have both potential and kinetic, right? But we can talk about that one. Right. So like I said, you can apply it to the entire system or you can break it up, right? It doesn't matter either way. If you break it up though, Now you've got a tension force here, right? So you need to determine whether or not that does work. For problems involving pin connections, right? Or pulleys and blocks connected by inextensible cords, right? Internal forces occur in pairs that are equal and opposite. Right? Points of application of each pair move through equal distances, and therefore the net work from internal forces in these cases is 0. Work on the system reduces to the work of the external forces. Right? And so remember, for problems like this, we've done problems like this, right? Where we had to use our cable kinematics, right? Where I know that there's a fixed length of cable there. And if I take the derivative of it, I get the velocity of that, right? I can take the derivative of that and get the acceleration of that. Okay. So the forces at B don't do any work. We've seen that, right? In this case, the tension in the cables don't do any work, right? They travel through the same distance. They have the same force. They're equal and opposite, right? The contact force here, right, does not do any work. We can talk about conservation of energy as well, right? And we did it a little bit to explain conservation of mechanical energy, right? To explain why the solid cylinder, which is the base before the hollow cylinder, the pipe. Some people call it a pipe, right? So let's talk about this in terms of this slender rod. We've seen this slider type mechanism in a couple of problems before, right? And so if I start at the top and then I drop it, and at some time later I come back and I look at it, and this has moved to here, this will have slid over by some distance, right? So I can express the work of conservative forces as the change in potential energy, right? And the principle of work and energy turns into a conservation of energy equation where we've got T1 plus V1 is equal to T2 plus V2, right? In this case, my initial kinetic energy and potential energy is 0 for both of these, right? Because I started at my datum. Now remember, when we're doing these problems, it's very important for us to define a datum. What is a datum? A datum is just some line, some point in space that we're referencing everything to, right? So if we pick it right, like in here, I can set all of my initial potential energy to 0 because there's no change from that point, right? At point 2, I've got kinetic energy, right? That's going to be 1/2 mv squared plus 1/2 omega I omega squared, right? And we're talking about the bar itself, right? We're not talking about the endpoints. We're talking about how does this bar, how does the center of gravity of this bar move with respect to my datum, right? Well, we would need to know that angle, right? But we could figure it out. How is this, how much omega do I have? How much V do I have? So by going through this equation here, right, and understanding that the I here is 1/12 ml squared, right, which we would get from the table because for a bar, that's what it is. And, that's one of those ones that you'll try really hard not to remember, but it shows up everywhere, so you probably just end up knowing it. Right, so V2 is 1/2 WL sine theta, right, so that's my potential energy, right? Potential energy is the weight of this, L sine theta. So I can plug it in, and I can solve for omega in terms of theta, right? So if I know that angle, turns out that I know the angle, and I know the length of my bar, I can figure out what omega is. Figure out what omega is. You guys okay on conservation of energy, right? Remember what voids conservation of energy? What voids it? Anytime that you see that we're using friction or there's any force in there that's not a conservative force, typically friction for these problems, if they say that friction is included, you cannot use conservation of energy, right? Why? Because friction converts mechanical energy into heat. All right, what about power? Power is the rate at which we do work, right? So it's the derivative of work, right? Or we could say du dt. Well, that's just the force times the velocity, right? Because the force is constant. And if we typically have force times the change in x, right? Well, force times x is my work. I'm going to take the time derivative of that. Force will stay constant. I'll get dx dt. So it's force times velocity. That's for translation. What about for rotation? Well, for rotation, it's just the moment times omega, or torque times omega, right? So again, it's the torque times the angular velocity, right? The moment times the angular velocity. All right, you guys have any questions on power? It's a sweet picture, right, of motorcycle wheel. It screams power, right? It screams power. Okay. All right. Why don't we just do one already? Right? Fine. We'll do it. Okay. I've got a drum and a flywheel where I is 10.5 pound-feet seconds squared. I've got bearing friction that's equivalent to a couple of 60 pound-feet. Well, that's a rotational friction, right? We'll talk about what that means in a second. At the instant shown, the block is moving downward at 6 feet per second. I need to determine the velocity of the block after it has moved 4 feet downward. So first thing that I key in on, I have bearing friction. Bearing friction tells me that I cannot use conservation of energy. I have to use work and energy here. Conservation of energy is off the table for this particular problem. Okay? Off the table. So what type of problem is this? Let's start there. What kind of energy? Kind of gave it away, but what kind of method would you use for this? Yeah, work and energy, right? You use work energy, right? Why? But why? Why should we know that, right? The things we should be keying in on to know what kind of problems. It's not asking for forces or accelerations, right? It's asking for velocities, and it has given us velocities, right? And displacement. We're asked for displacement, we're asked for velocity, right? We should be using work energy. Okay, so work energy problem. How are we going to start? Well, the best way to start, right, is we're going to draw our state diagrams, right? So I'm going to have state 1 over here, and this is going to be 1.25 feet. I do have forces at this pin, right? I've got AX and AY. I know that this is going to be rotating with some omega 1. And in the position shown, right, we're going to have this block hanging here. And initially, this block has the velocity v1. Right, we'll set our coordinate axes up here so we can see them. Ooh, almost tripped. I also know that this mass here is 240 pounds. And I'll write that there. Okay. I'm going to set my datum. I'm going to set my datum as the center of mass of my mass, the center of mass of my block here, right? And we can talk about state 2. What is this going to look like after it has moved, right? In state 2, this will have some velocity, v2, right? It's still 240 pounds. We know, right, we are told that this will have moved by 4 feet, not 4.5 feet. Problem statement told us that this moves 4 feet. And just so we remember, this is the data, right? We're measuring everything from there. This is still the same. -2. Okay. Right, so that's what our state diagram looks like. And this is helpful, right? This is going to be helpful for us because it's going to let us know, it's going to remind us, right, about do we have any potential energy? What kinds of kinetic energy do we need to account for? All of those things. There's one thing that I haven't drawn on here, right, which is that bearing friction. That bearing friction. So let me draw that on here. Moment for friction, M sub F. So in this case, right, when you're told that you have a couple tells us that we have a moment, right? It's two forces, two frictional forces that are equally separated, and so we can collapse them, and their effect is a moment, right? That's what a couple is. So M sub F, all right? Let's write down what we know. What is the problem? What has the problem told us? Well, I is equal to 10.5 pound feet second squared. I was told that V1 is 6 feet per second and that M sub F is equal to 60 pound feet. That's what I know. Not seemingly helpful. Well, some of it's helpful, right? I know I is going to be helpful. But having V1 doesn't seem super helpful, except that, right, what do we know, right? What is the equation that we're trying to use here, right? We need to discuss the principle of work and energy, right? T1 plus U from 1 to 2 is equal to T2. That's what we need to know. So I need the total initial kinetic energy of this system. And this system is translating and rotating, right? So I need to figure out both. So T1 is going to be 1/2 m v1 squared plus 1/2 I omega 1 squared. Let's do it, right? Well, what's omega? Because I'm not given omega 1. So how am I supposed to find omega 1? Seems problematic. So let me ask you guys this. I'm using my water bottle because that's pretty circular. I've got this here, right? And I've got a string here, and I'm going to pull this string with a known velocity. How fast does this mean that this is rotating? How would you figure out how something's rotating if you know the tangential velocity? There it is. Remember, omega 1 is equal to v1 divided by r, right? Because this velocity is a vector, I can translate it anywhere along its line of action, right? It's connected by that cable. That cable has to be moving with v1. Everything is moving with v1 at that point. So I can figure out omega 1 from that. Right? So now I know everything in the first part of this equation, right? So I can write this as T1. Let me do this. This is equal to 1/2 times 240 divided by 32.2, right? Because we're given the weight, times V1, which is 6, times 6 squared, plus 1/2 10.5 times 4.8 squared. And so I'll write it up here so I don't run out of room on the side. So T1 is equal to 255.1 foot-pounds, right? So that gives me T1, right? So I can do the same thing for T2. So that's what we're going to do, right? That's what we're going to do for T2. So let's do that. So I want the kinetic energy of 2. Well, this has to be 1/2 m v2 squared plus 1/2 I omega 2 squared, right? Well, bad news is that this is 1/2 240 over 32.2 times v2 squared, which I don't know, plus 1/2 of 10.5 times v2 over 1.25 squared. Right, so I have to live with this equation here. I have to live with this one. I can't do anything. Remember, we're trying to find V2, right? That's what we're looking for. So we need to tie this together using our U from 1 to 2. But Dr. D, we didn't do anything with the potential energy, right? Well, the equation doesn't call for potential energy. This is not conservation of energy. Now, the potential energy is going to come into play because of the work. Okay, the weight of that object is going to cause work. Right? It's going to cause a rotation. Right, so let's talk about that. Right, but first let's rewrite this as 7.09 v2 squared. Right, so I just took all my stuff. And so T2 is equal to this. So the only term that I don't have, right, I have T1 and I have T2, but I need the work, right? I need the work now. So how are we going to find the work? Well, remember, work from 1 to 2 is equal, in general, to the force times the change in distance plus the moment times the change in angle, right? So what do we have in this, right? Well, I talked about it a little bit, just a second. We got the weight. So how much is the weight moving? And how much is the weight moving? Right, so how do we find x2 and x1? Well, we know how much the weight moves, right? We're told. It moves 4 feet. So straight up, we were told that. Excellent work. You did it. Okay. My moment was in the negative direction, right? So here, in this case, the frictional moment does some work. Okay. And it is doing work that is fighting the motion. Okay. Why is this different than friction at a wheel without slipping, right? The wheel without slipping, there's no change in velocity there. There's no change in position, right? Velocity is 0, meaning that the position is constant. In this case, the angle is we're gonna be fighting this angle, right? So we need to figure out what theta 1 and theta 2 are. And so theta is just x divided by r. Okay. In this case, theta 2 would equal x2 divided by 1.25. Well, x2 is just 4. So we can figure out what theta 2 is. Theta 2 is 3.2 radians. Okay. Where does that come from? I mean, we've talked about this before, right? If we're rotating, right, the linear distance that something travels, right, is related to the circumference. So if you did one rotation, right, we would say that this mass in one rotation would have traveled a length that is equivalent to the circumference of the circle, right? And we create this ratio of 2 pi r. 2 pi r over theta is equal to x over x over s, or whatever we called it, right? And it simplifies out to x over r. Theta is equal to x over r. Another way of thinking about this is, right, if you took the derivative of this, you get omega is equal to v over r, right? That's where it comes from. Okay. We're going to assume that we're starting at 0 angle, so we'll get 3.2. All right. Is everybody okay so far with how I came up with it? That distance x2 minus x1, I think, is pretty clear where that comes from. Are we cool with the 3.2 radians? We want to talk about it. No. I know the weight, right? 240 times 4 minus 60 times 3.2. U from 1 to 2 is equal to 768 foot-pounds. T1 plus U from 1 to 2 is equal to T2. Enter my things. 255 plus 768 equals 7.09 V2 squared. So V2 is equal to 12.01 feet per second down. Everybody okay? Do you have any questions? Questions? Everybody good? Maybe? You know? I would very much recommend, when you're doing these types of problems with work energy or impulse momentum, first thing, draw your diagram. Second thing, write out your equation for principal work energy. See what you need, right? And figure out what your initial state looks like, what your final state looks like. Most cases, right? Most cases, we tend to ignore friction in most cases, right? Especially when we're doing first passes on things. So most of the time we can use conservation of energy. But if you do see something talking about friction, we're going to have to figure out the work. Right? Have to figure out the work. Okay, so here's one. I believe we've done something like this at some point. Let's see what's going to happen. What time is it? We'll start this. Work on this for a little bit. All right, so I'm starting my system at rest when a moment of m is equal to 6 Newton meters is applied to gear B. Right, so I'm driving this with a torque, right? That's how we can think about this, right? I'm going to be applying some moment, some constant moment at gear B, and that's going to drive gear A. I'm going to neglect friction, solid. Always like to see that. And I want to A, determine the number of revolutions that gear B before its angular velocity hits 600 RPM. And B, I want to find the tangential force exerted by gear B on gear A. And look, I'm given MA, MB, KA, and KB. Man, it's been a while since we've seen KA and KB, right? Those are radii of gyration, right? Radius of gyration. What can we use that for? Well, if you know the radius of gyration, you can find I. We'll talk about it in a second. You find the mass moment of inertia by using K. Right, because I is equal to K squared times M. I is equal to K squared times M. Okay. 20 minutes, huh? We'll start it. Yeah, we'll start it. How do we start it, right? Well, we're going to do our state diagram, right? And Dr. D is going to do something on this one, right? What's state one look like? Well, I'm not going to redraw state one because it's at rest. It looks exactly like the picture on the other slide. There's nothing interesting happening. Everything's zero. I'm just going to draw two circles. All right, so state one is at rest. Therefore, diagram is not interesting. There, I said it. People of the internet, fight me, at me. I think I used that right. Kids still say at me? I don't know. All right, state two. All right, I've got gear A, which has a radius of RA. And I've got gear B, which also has a radius of RB. Gear B has some moment being applied to it here. We'll call it M. And we know that if we're applying a moment like that, we should expect to have some omega this way, right? So if I'm torquing this counterclockwise, I should probably expect to get a rotation counterclockwise, right? And if this gear is moving counterclockwise, then this one should be moving clockwise, right? Because gears, there they are, gears. It's beautiful, right? Meshing gears. And so if one spins this way, the other one spins the other way. Right? That's how gears work. Last time I checked. All right, so what do I know? What is known to us? Well, first of all, that MA is equal to 10 kilograms. We've got MB is equal to 3 kilograms. I've got KA is equal to 0.2 meters. KB is equal to 0.08 meters. RA is equal to 0.25 meters, and RB is equal to 0.10 meters. There's a lot of setup for this problem, right? Because I want to talk to you about what kind of motion are we dealing with here? What kind of motion are we dealing with? Yeah, it's pure rotation, right? That gear is not going to translate, hopefully. Hopefully they don't move side to side or up and down. So they're just going to rotate, right? They're fixed axis rotation. So we've eliminated half of the kinetic energies that we need, right? We do not need any translational kinetic energy here, right? It's all purely rotational, right? So if I write down, right, if we start with Dr. D's advice, and we write down the potential, well, the kinetic energy initial, right, plus the potential energy initial is equal, well, let's not do it that way, plus the work from 1 to 2 is equal to the final kinetic energy. Why aren't we going to use potential energy here? Right? Why aren't we going to use potential energy? Why don't we use conservation of energy? Why use the principle of work energy? The principle of work energy will always work, right? Will always work. We're given that moment to start with, and the only way that we can incorporate it is by figuring out the work. Okay? How do we figure out angular potential energy here? Right? Well, I mean, neither of these move in space, so that's just going to be 0. So we're actually going to be missing part of the story by using potential energy. There's no spring, there's no gravitational difference. So we're going to use this, right? So if I write this down, right, and I know that everything starts from rest, because I was told it does, right? Remember, state 1 is at rest, therefore diagram is not interesting. So T1 is equal to 0. Nailed it. Right, nailed it. Okay. Well, since I've got that, all right, let's talk about T2. Right? This is going to be what? 1/2 I bar A omega A squared plus 1/2 I bar B omega B squared, right? Isn't that lovely? Isn't that lovely? It sure is. But the problem here is I don't know omega A, and I don't know IA or IB, right? And that's where some of these things come in to help us. Okay, we were told what omega B is, right? We want to find out what happens, right, when omega B is 600 revolutions per minute, right? Woo! Nailed it. All right, feeling good now. Powered. I'll be good. I'm gonna fall asleep in a second. Wow. All right. Okay. Omega B, we were told, we want to find out what happens when this reaches an angular velocity of 600 revolutions per minute, right? Awesome. But RPMs isn't great for us. We'd rather have it in radians per second, right? So we can do the conversion. And if we convert this, it's going to be times 2 pi radians per revolution, right? Times 1 minute per 60 seconds, right? And we'll find that omega B is 62.83 rad per second. That's what we'll find out. Okay. So great. We have omega B. We don't know omega A. More on that in a second. We'll talk about. Let's find IA and IB, right? Because I told you guys we can find IA if we know KA because it's just KA squared times MA. How are we supposed to remember that? Well, great question. You're going to be given the equation on your equation sheet because that's one of those things that you should just look up, right? So we can calculate these really quickly. 0.0192 kilogram meter squared. Right? So hey, look at that. I got IA and IB. And what would you know? IA, since it's a larger gear, it's going to be harder for us to rotate it than B, because IA is larger than IB. Great. Now we need to figure out what omega A is. Right? So let's do that. How am I going to figure out omega A? What do we know about gears? Now, I don't remember if we've talked about this previously in this class, or if you've have you guys taken the class with Professor Higgins where you take apart like all the machinery and stuff? Yeah. Where you take apart like the paper towel thing? 302, yeah, 302, that's all. Well, you should know, Brendan. If I have gears, right? How do I transform? How does having 2 gears of 2 different sizes change the amount of velocity of each gear. So if I have a small gear and I'm applying like 62 point, what did you say, 62.83 radians per second of angular velocity, I'm spinning it at 62 radians per second. How fast is the larger gear spinning? Would you expect it to be more or less? Be moving slower, right? And yes, right? And so, how do we characterize that, right? Well, we talk about this thing, we call it the gear ratio, right? And when you have the gear ratio, you understand how the torque gets transmitted from one gear to another, or the speed gets translated from one gear to another, right? So because of the gear ratio, omega A is just the gear ratio, which is the radius of gear B divided by the radius of gear A times omega B, which gives me 0.1 over 0.25 times 62.83, which gives me 25.13 rad per second. Now I have everything to figure out T2, right? Now I have everything for T2 because I can have 1/2 IA, which is 0.4, times 25.13 squared, plus 1/2 times 0.0912 times 62.83, and this gives me T2 is equal to 164.2 joules. I have T1 and I have T2, right? We will find the answer to part A for this problem, and then we'll wrap it up in class on Friday, okay? So the last thing that I have to do now, right, because I know T1 is 0. I was told that there's no kinetic energy to start with. I was told I found T2, right, because I understand the gear ratio, right? Maybe you don't, maybe that's the first time you've seen it, and that's fine too. But remember, right, think about it. If you had it, everybody's played with gears at some point, right? And if you've got a small gear moving fast, the large gear is going to move slower, right? The large gear is going to move slower. That is the gear ratio. Gear ratio is the radius of one divided by the radius of the other. Right? Another way of thinking about it is where they're connected, they should have the same velocity, right? So VA at the connection point and VB at the connection point, the tangential velocities will be the same. What is tangential velocity? Well, it's angular velocity times r, right? And so you can generate it from that. All right, so work. Work is the last thing that we need to talk about. So what is doing work here? Well, the only applied force that we have is the moment, right? Is the moment. And the moment times theta 2 of gear B minus theta 1 of gear B. Okay, I know that my moment was 6 times theta of 2b, right? Why? Because theta 1b, we're going to say we start at 0, right? When given the option, we should always say that our initial position is 0, right? Why? Because we don't really, for work, we don't care. We only care about the displacement, right? We only care about how much we've moved. We don't care about the absolute position, like it started at 5 degrees and it moved to 45. No, we care that the difference was 40. So if you don't know, and you just need to know the distance that it moved, set the beginning one equal to 0, right? It's fine. So we're left with this, and that seems somewhat problematic, except that we remember that we need to know how many degrees this moves through, right? That's what we were looking for. So our equation that we started with becomes this, right? Because T1 is 0. We can say that 6 theta 2b is equal to 164.2 joules. And so theta 2b is equal to 27.4 not 24, but 27.4, 0.4 radians, which is 4.36 revolutions. Okay. Part A asked us to find the distance, the angle that we would travel through, the number of revolutions that it would take before our velocity increased to a certain speed. And that's what we just found. All right, we're gonna pause this problem there because I don't think we got like 5 minutes left in class, and we'll do part B as a way of recapping next class. We'll also talk a little bit about CLCs, right?
Are you assigning groups for those?
No, you guys are gonna self-assign. There's 9 of you, so I would like 3 groups of 3. 3 groups of 3. We'll talk more about it on Friday. Okay? Friday is gonna be mostly us doing problems, and when I say us, I mean I'll probably finish this one at the beginning of class, and then you guys are gonna work on problems. I'm gonna walk around, maybe bring in a hammock. I don't know. Figure it out. Nathan, you have a question?
Yeah, when, so I know we get that like week before the end of class, like kind of wrap everything up. Like when would you say would be a good time to get like, get moving on the
We'll talk about that on Friday for sure. I would say, so the way that it typically works is the lab step. So I don't know what the print volume is going to look like. So we're going to want to get our prints sent to the lab staff as soon as possible. So the sooner the better for you guys to settle on the design and create STL files. But we'll talk more about it on Friday, and then you guys can start throwing designs around as a group and things. So that's all I've got. I'll see you guys on Friday. No office hours today because I have a meeting that I have to go to at 3. But office hours are the same on Friday, 3 to 5. Or if you need me at different times, right? Use Discord, reach out, let me know.
So you talked about the Sharpie impact set. The materials too, we're doing a lab on it. I was wondering if we have a full size Sharpie impact test or just a small scale one.
That's a great question. I don't really know, honestly. I always assumed it was the full size one.
Somewhere.
Yeah.
That's cool.
But if it's the one it's down there.
Yeah.
So I don't know. I might just not know, which is fine. I've not taught any of the material stuff, so that's a Dr. Staggs and Dr. Wright special.
Yeah, it's pretty interesting, yeah.
They get mad at me because I constantly tell everybody that as a mechanical engineer, you really only have to choose between 2 materials, steel or aluminum. But
Especially because half the lab equipment doesn't work with the torsion tester and a couple other.